Right. So before we start there, I just want to remind you that the midterm's due tonight at midnight. As I mentioned to you, we can't really give deadlines, but if you're very desperate, if you say, look, for whatever reason, then we can have a slight extension, but try and get them in before midnight, because then I can mark them. But as I mentioned, if you're really stressed or something like that, then you can write to me in there. But as I say, try and get it in, that's good. So another reminder is that the unit summary for the brew is due on the 16th, and a few of you have written about the sensory class. You don't need to include the sensory class on that. So it's just the brewing unit I gave. And for both 3260 and 3270, and the 3270, the brewing case study is due on the 19th, and the lab for the 3260 people, because there's no simulations now, you've done all your simulations, that's due on the 19th as well. All right, that's good. Yeah, I think that's all right. All right then, without much more ado, because I'm getting behind as usual, I'm going to just like I said, I'm on the old computer again. Oh yeah, I cannot get most of the links to work for the beer case study. Yeah, I found it unusual because I went through them and it seemed to work all right. So I'm wondering if it's a copy and paste kind of syndrome, or maybe the links have been blocked. I'll try them out again, or get the TA to do it, isn't it? To actually try it. But I tried most of the links and they seem fine. But if you do have problems, I'll try and suss it out afterwards. That's good. All right. So when we left it last time, we're talking about water and how valuable water is. Essentially, water restricts the growth of guelph for a few years, but then they kind of started water management, which is the efficient usage of water in order to expand. And we'll talk a little bit about that if we get to water recycling and how Guelph overcame its water problems. Now, in California, they've been in a drought now for about 7 years. Well, it did break a little bit last year, but essentially been in a drought situation, as has Australia. And as I mentioned to you last time, water is going to be the new oil, in that it's going to be the most precious resource, and you can imagine wars and everything going to be sort of fought against it. But anyway, before we say doom and gloom, water in fermentations is critical. We use it for all kinds of things, not just the fermentation medium, but also sanitation, cooling, and other sort of activities. And because we use so much water in the fermentation business, and we're not, we're talking beer, wine, whatever, but citric acid, any fermentation, we need a sustainable supply. Now, as I mentioned to you, obviously most of us get the water, and especially industry, get water from municipal supplies. You think, well, that's safe, isn't it? But regardless of whatever food sector you go into, be it fermentation or food production, you always test the water, because things go wrong and they could certainly affect the performance of your fermentation, in addition to other things as well. And we talked about how we do water analysis. We talked about the microbiology of it, then the chemistry in terms of looking for those pollutants and the volatile organic carbon. And then we got to the point, simply, of talking about ions. And ions are difficult because they're difficult to remove, as you can imagine. And these are the pollutants. So when we talk about some of the most polluted rivers in Canada, for example, invariably they kind of end up being near agriculture or industry, because this is where you get the runoff of ammonia nitrate. And with industry, you get all kinds of pollutants going in. So I left it with this sort of table. Well, it's not even a table, is it? I left you here. So just to confirm, we've got regulatory limits, which for ammonia is 0.05 ppm, or mg per litre, if you want to call it that. And these are the toxic limits, because ammonia is toxic, and that's 0.5 mg. And we talk about nitrates, nitrites, phosphates, chloride, iron, which obviously is very staining, rusting, and it actually promotes biofilms, and urochrome, which is a breakdown product of hemoglobin, which is found in urine. Well, hemoglobin is found in the body, but typically if you find urochrome, that usually means you've got a septic spillover, or someone's been pumping raw sewage into the St. Lawrence again. So these are the ions we look for, but we also look for water hardness, and water hardness is significant for the reasons we gave really through brewing, isn't it? Is that in brewing, the water hardness does affect the product, but ordinarily water hardness is not a benefit. It is if you're brewing, but not so much if you're making anything else, because of scale, because it interferes with sanitizers, and it can affect the product negatively as well. Now, we measure hardness, as we mentioned, in degrees of hardness, which is kind of the grains of bicarbonate, which is the old one, but people like to kind of stick to the old sort of scale of 1 grain. But obviously, that doesn't really mean we should do today. So 1 grain is about 18 ppm, or 18 mg of calcium carbonate. And we define the water based on the degrees of grain, or of the amount of calcium carbonate, and it goes from soft to very hard. So in Guelph, for example, we've got hard water. I don't know if it's very hard. And the way we determine water hardness is through a titration. This titration is using a chelating agent called EDTA. And so what you'll find, it goes from red to blue, and then you know how much equivalent bicarb you've got, or carbonate you've got, to define the water hardness. And as I mentioned to you, apart from brewing, and even in brewing sometimes, water hardness is a negative, not a positive. So as we talked about in brewing, we've got 2 kinds of hardness. We've got the carbonate hardness, which is temporary. So when we look at temporary hardness, this is what can be boiled away or precipitated out. So, typically when you go to high school, you'll learn, say, oh, it's just what's boiled out. But, calcium bicarb isn't exactly volatile, is it? Well, the bicarb is, but the calcium isn't. So we have the temporary hardness, which can be removed by boiling or precipitation. But then we have the permanent hardness, which are the calcium, salts, magnesium, chlorides. And what these are ones that remain in the water. So these are 2 types of hardness that we encounter. Now, as you know from at home, you've got a water softener, and if you haven't got a water softener, your kind of pipes start clogging up and things like that. And in industry, what happens is they'll reduce the water hardness, and they'll do that by ion exchange columns, which strip out the calcium. If they're really posh or already got some investment that can do, they'll use reverse osmosis, which essentially, as you know, it strips the ions out of the water completely. But what we tend to do, isn't it, is add the sodium carbonate or calcium hydroxide as opposed to sodium carbonate, isn't it? The water softener, so they can never tell. But calcium hydroxide works by using the calcium to take out the bicarbonate, very much like brewing when we talked about making the water, isn't it? And with sodium carbonate, what happens is the sodium displaces other calcium salts, so the calcium precipitates so the calcium reacts with the bicarbonate to produce calcium carbonate, which precipitates out. So one way or another, you're taking out the calcium and then the bicarb, aren't you? So that's water softness. I think I've just said this one anyway. All right, so as I mentioned to you, apart from brewing, water hardness is really a negative, but why is that? Is it because it will affect the flavour of the final product? Is it because it neutralises detergents, scales, precipitates medium constituents? Does it inhibit microbial growth? So you click which ones apply. All right, so water hardness, as I mentioned to you, is perceived as a negative, but why is that? All right, have a look, see what we got. Yeah, basically, when we say it affects the final product, I suppose it's misleading in a way because obviously beer is a final product and it would affect that. But other fermentations like citric acid production, antibiotic production, glutamate production, it wouldn't affect it. But it does neutralize detergents and sanitizers. And you'll notice this if you have a bath and you've got some soap and you're in soft water, it gets nice and foamy. But in hard water areas like Guelph, it'll just like be a scum on the surface. There you go. If anyone has baths these days. It obviously accumulates scale, which causes clogging, heat exchangers be affected. And it can also precipitate medium constituents, which can lead to nutrient limitation of the ions the microbe needs. So it's those three, sure. All right, so that's water. And like I mentioned to you, we treat water coming in. If it's been municipal, we just check it. But there are places, certainly I would imagine most of the industry in fermentation, a bit like Sleeman's, they'll strip the water out and reconstitute it. And I imagine that happens in a lot of places. And don't just let the water come from municipal supply straight into the facility. And I was in a marijuana grow-up, a legal one, just last year, and they bring municipal water in, but they deionize it, they ozonate it, and then they put nutrients. So even those grow operations treat the water before they actually use it. But the consequence of using water is that we get wastewater. And, you know, if someone said to me what the business to be in, I would say to you, wastewater management is the kind of key thing. There's so much opportunity in wastewater these days that you could really, and it's a shame because, you know, when we go to the wastewater plant on these sort of field visits, you can get to talk to the graduates who went into wastewater, and you could ask them what it's like. And it is one of the big growing businesses. So not only in terms of working for, say, the city, but even small businesses. So if you don't get into vinegar, get into wastewater. And the reason why wastewater has really taken off as a business is because of the sort of fines, surcharges, levies, whichever you want to refer to it. So not so many years ago, well, 15 years ago, which is quite a long time, it used to be if you were found dumping high organic loading into the municipal sewage system, you would get about $100 fine a month. And many businesses said, well, it's cheap, isn't it? So we'll keep using it. But then suddenly, not so many years ago, the Ministry of the Environment started coming round giving red cards to industry. And red cards are like what they suggest is that if you're found guilty of putting high organic loading or high polluted loading down the municipal sewage system, you can get closed down. And I think these processors were really shocked when they got these red cards because they had 30 days to fix things. But now what happens is that you get heavy fines, and we'll talk about that. So with wastewater treatment then, every facility I know has their own wastewater treatment. And there's lots of options in wastewater treatments, as we'll talk about. And a lot of it depends on the nature of the waste we're going to get. And what we do is we characterize waste in terms of organic loading and volume. So with grey water, that's basically what we create every day. And it's very dilute, as you can imagine, and it's relatively easy to treat. And you know what we were talking about last time about water sustainability. There's definitely a move, and I wouldn't be surprised if in a few years we'll be drinking back the water we just disposed of. I could imagine a time where every home will have a water recycling unit, but we'll see, isn't it? Then we have stormwater, which is basically what we're going to have in the next few days because everything's going to melt, isn't it? And that's very diluted, but it's very high volume. And that really does cause issues with the top water plant, for example, because as we'll see, when you've got very diluted organic loading, the biological processes suffer. For the simple reason you need quite a lot of organics. I know it sounds counterintuitive, but you need a lot of organics to sustain an aerobic digestion process. So we'll come to that as we go to it. And then you've got industry, which has obviously a wide variety from low pollutants to highly toxic constituents. And as I mentioned, if you visit the 10 most polluted rivers in Canada, most of those are by industry. I think the worst one's in Quebec, but I can't remember what the actual place was. So in wastewater treatment, then what we're trying to do, isn't it, is that we're trying to get rid of these chemical pollutants because we have to put the water back into the river and lakes. And that means we have to get rid of the chemicals. But also, as you know, from why beer and wine got so popular, is that waterborne disease is fairly significant. It's the biggest killer, one could say. And we have to get rid of the microbial contamination. And with fermentations, you're generating a lot of wastewater, which is going to be very high in organic. So you typically would have your own wastewater unit. And really would just put it straight down the municipal. Even Wellington Brewery, they, in the end, got their own wastewater treatment. And it's a shame we couldn't go on the field trip because they've got carbon dioxide capture as well. They've got really high tech at Wellington Brewery. But if you go up there one day when everything's done, you can ask to see it. And so basically, every facility has its own wastewater processing plant these days, or facility, whichever you want to call it. And the reason for that is because, as you could imagine, when we're doing fermentations, we generate a lot of organic loading. And we talked about the BOD last time and COD. And as I mentioned to you, when you get spoiled beer, it's a real headache because you've got to dispose, not only have you lost your fermentation, but you've got to dispose of this really high BOD. And the regulations say your BOD going down the municipal sewer can't be any more than 300 milligrams or 300 ppm. And as we talked about with BOD, that's the oxygen consumption over 5 days at 20 degrees C. And so it really does cause a few headaches when you get a spoiled batch of beer and you've got to get rid of all this BOD. Now, typically after treatment, you would get around about 10 to 20 mg or ppm BOD. And the way we treat it really depends on the volume, the characteristics, and what sort of footprint we have, which we'll talk about. We won't jump ahead, will we? So the reason why these have these strict regulations is because of pollution. So you've probably all seen different rivers and that which have been polluted, and you say, well, there's no fish in here. Well, there's no fish in there because all the oxygen's been depleted. And then what you get is, hang on a minute, I've just got to pause it a minute. Yeah, so as I mentioned to you, you've seen polluted rivers, you know, where you've got no fish in there and things floating. And the reason why pollutants are such a hazard is that they deplete the oxygen and they introduce obviously chemicals into the river that affects the wildlife. And as we mentioned right at the start of this unit, what happens is that water is recycled. So even if you pollute rivers, well, that river's going to go to maybe your next drinking water. So there's all kinds of reasons why you don't want to pollute rivers, isn't it, to sustain the environment. And typically with water pollutants, it is to do with not only the microbial loading in terms of pathogens, but also those elements or nutrients that would cause algae blooms. So if you live near Simcoe, I think it's Simcoe Lake, isn't it? Yeah, in Simcoe Lake, they have an experimental lake there where they actually do grow blooms. So they'll basically feed in different nitrogen and phosphate. So you'll see this big bloom. The blooms deplete the oxygen. It produces biotoxin, which isn't good. And so you've got all these organic loading, which supports blooms. And you've got the heavy metals, the mercury, the lead. And then what we call halogenated organics, which are byproducts. So things like bromides, chlorides, fluorides, all these are halogenated organics, which essentially are carcinogenic, toxic, and they also leave taints which can't be easily removed. And so you get dead zones where you get algae stimulation, oxygen depletion. So when we're looking at recycling water or treating wastewater, we have to, it is a bit of an engineering exercise for definite, but what we have to do is we characterize it. And the characteristics of a wastewater is the volume, you know, how, what's the kind of volumes you have to treat per day. The BOD, which we talked about, the biological oxygen demand, and the COD, and the total soluble solids. So we talk about waste as good quality and bad quality. And good, oddly enough, when we say good quality, that means it's really heavily densely loaded. So it means that you've got high BOD, high COD, high total soluble solids, and the volume is what the volume is. And it depends on what, and that's what really makes us decide what kind of wastewater treatment we're going to do. So if we've got very high BOD and COD, especially BOD, what we do is we can use a biological process, and we'll talk about this now, where we convert the carbon, phosphates, and nitrogen into biomass, which we then refer to as sludge. But we'll do that at our sort of simple pace. So with wastewater treatment, then what we have is different treatment. So we've got physical treatment, which is the sedimentation, screening out of particulates, insolubles. Then we have chemical treatments, which we talked about before, you know, getting those ones that are soluble in water, and then we make them insoluble by coagulating. And then biological treatment. And in biological treatment, what we're doing is that we're actually taking the carbon, nitrogen, and phosphate and converting it into biomass, which can easily be removed because cells are easier to move than small molecular weight compounds. And we can do it aerobically or anaerobically, as we'll talk about. So what we're going to do now is talk about municipal sewage treatment. And in some ways, those small wastewater treatment plants within facilities share some similarities, but they're different as well. But we'll talk about the sewage treatment first, and we'll go on to talk about the smaller units. So what we do, we have our sewage arrive, and then we try to screen out as much as we can. And like I mentioned, it's a shame we couldn't go to the wastewater treatment this year for the simple reason you could see these screen filters, and it's amazing what sort of stuff people throw down drains. And I think they mentioned they get 2 or 3 dumpsters a day where they literally everything that's like, well, it's mentioned too many details. Should we say things that have gone down the drain tend to then be disposed of. So you try to remove as much, and then you hold it in basins so that the particulates will sink down, you know, sedimentation. And at that point, what you'll find is the fats and lipids, they rise to the top where you skim them off. So you get this sort of particulate sinking, fats floating, and then you skim them off and you kind of decant the sediment. But then what we do is go through different treatments. So typically what you would have is the water would go through this oxidative treatment called activated sludge or trickle filters. So typically when we were allowed to go on planes all those years ago, when you come down to land in Toronto, for example, you can see the wastewater plant there in Mississauga. And you'll notice these sort of cylinders, and they're the trickle filters, and the big sort of lagoons, what look like big tank, well, not tanks, but big basins, they're the activated sludge. And in the oxidation process, what we're doing is we're taking the carbon, nitrogen, and phosphate elements, and then incorporating those into microbial cells because they're growing. And then once the microbial cells have grown, they are referred to as sludge. And we need to digest the sludge, because if we have all this high volume of sludge, we've got another problem with how to dispose of the waste. So what happens then is it goes through the anaerobic process, which breaks down the sludge and also the sludge sediment from the settling tanks to produce methane. And that's where you can see fires burning brightly, or not so much these days, but it's reclaimed. And other things like that. So we'll go through this in painful step by step. I'll try and not dawdle too much because I think we get bored. So the first thing we do in water treatment is try to remove as many of the solids as we can. So these are insoluble, that's how they precipitate out, and that gives us sediments that can go into the anaerobic digester to break down to methane. Now, the activated sludge process gets oxygenated, and the reason why we're oxygenating is to really increase the metabolic activity. So, well, I suppose you know this, but essentially, with oxidative metabolism, you end up with CO2 and biomass, isn't it? But with anaerobic, you really only end up with an incomplete oxidation of them chemicals. Even though you can do anaerobic, it just takes time. So the reasons why the aerobic treatment performed is because it's more rapid. And not only is it more rapid, but we tend to drive off the volatiles, i.e. those compounds that give sewage a smell. And also we can convert it to CO2 and biomass. So essentially we've got this aeration then, and the aeration then get passed into this post-clarification basin where essentially the sludge, i.e. microbial biomass, settles out. Now, what you'll hear a lot about is about the settling characteristics of sludge, and I'll talk a little bit about it later on, but I might as well say it now whilst I remember, is that when we characterize sludge, we say it's good settling or bad settling. So when it's good settling, it basically sinks down and it separates out, a bit like yeast does in lager production. But if it's poor settling, or low settling, it's a bit like ale yeast. They kind of keep suspended. And as you can imagine, when you've got poor settling, that's a big problem because you're keeping the nutrients, if you like, in suspension. You're not really affecting the BOD so much, are you? So you want good separation because then you can decant the water out. You can coagulate it or put it through a tertiary treatment, chlorinate it, dechlorinate it, and then put it into the river, which then we can drink it again later on, isn't it? And the sludge from this basin goes into this anaerobic digester, which breaks it down over 2 weeks into methane, hydrogen sulfide, and CO2. And once the anaerobic digestion process is complete, we take the biosolids, we dewater them, and we can inject them under the ground, or we can do what we call broadcast, which is basically spread them onto the land. And I'm pretty sure if you live in the country, you know what broadcast smells like. Is that it does definitely make a change to the air. It does smell a lot. That's why people put it on the ground. And there's this big debate. A debate goes on what's better, to actually spread it onto land where it kind of decays much quicker, but you know it does give smell and it does cause runoff into rivers, or inject it where the decay is much less, but obviously you don't get the smell or you don't get the runoff. So it's a big debate about that. Anyway, we'll go through these processes in turn. Well, I think I've said this already. Oh yes, and so I've gone through wastewater treatment, but how does the treatment of drinking water differ from wastewater? Is it because there's no settling stage, no coagulation step, no biological digestion step, no chlorination, or both treatments are exactly the same? So how does drinking water treatment differ from wastewater? Is it because there's no settling, no coagulation, no biological, no chlorination, or are they the same? All right. Oh, interesting. Yeah, and this is important because people do get confused by the two. With potable drinking water, essentially it's clean to start with. We don't take sewage yet and pump it in. And so there's not enough BOD, carbon, nitrogen, phosphate, whatever you refer to support microbial growth, because this is not the ironic thing, but the thing is for a biological step, you need to have high BOD. So that's where it differs. So wastewater has a biological step, whereas drinking water doesn't. All right then, so what we have then in wastewater treatment, these different steps. The primary step is the sedimentation. Then the secondary step is this biological activity where we're basically converting carbon, nitrogen and phosphate to biomass and CO2 in the case of carbon. And then we do this by aeration, physically by the activated sludge process, which is much more efficient than the trickle filter and more controlled. Because if you do become a wastewater manager, half the trick is just keeping this sort of process going. But it is a very fine balance. If you put in too much organic matter into these tanks, then you can get sort of abrupt changes in the sort of biomass and things like that. It can cause, and it does negatively affect the treatment, but if you put too little in, then you starve the sludge and it starts dying off. So it's a very fine balance, and you've got to look after your sludge, as I say. So the trickle filter system is more old, and we'll come through the trickle filter system with the example of vinegar, isn't it? But it's very, and I don't know what came first, that or the vinegar production, but we'll talk about that. Now, as I mentioned to you, sometimes if you've got fairly low volumes, you can actually go straight to an anaerobic sludge digester. And you've probably seen these. They call them biogas generators these days, where you basically put everything through this anaerobic sludge. So it's just an anaerobic process. It produces methane, which is a biogas, I suppose. But it takes a long time. It just reduces the amount of sludge, and it obviously generates energy in order to be used as a energy, or methane can be used as an energy source. And we can use the biosolids as a nutrient supplement in agriculture. And then the tertiary treatment is where we remove the fines. So, you know, once you've settled down the activated sludge process, you draw off the water, and sometimes you've got some residual organics in there, which you can coagulate out, or you can pass through what we call a contractor, which is a biofilm, which we'll talk about in a little bit. And once we do that, we basically can ozonate the water or UV treat it. If we chlorinate it, we have to chlorinate, then dechlorinate. And we typically chlorinate at 3000 ppm. But even then, the viruses survive. I remember doing a sampling visit to the sewage works in Kitchener, and in Guelph as well. And it's amazing what you find in the effluent going into the river. You get viruses, Clostridium difficile, and it just spreads everywhere. But anyway, so you chlorinate it, dechlorinate it, so then you release it into the rivers, keep the water balance. So in terms of the primary treatment then, it's just basically screens. And as I mentioned, you get rotary screens and it just collects everything. You can get these settling tanks, which are obviously V-shaped because you want to concentrate the insolubles in the bottom. A very slow process for sure. And once you've collected them, as I mentioned, in Guelph, what they'll do is just put them in a dumpster because it's not, should we say, it's not biological what they usually find. It's the opposite, that you just dispose in landfills. But then what you do with the rest of it, you want to get it to settle. If it's floating, you want to break it up so you've got maximum surface area for the microbes to act. So you'll use these kind of big blenders. I haven't seen these in Guelph, but they kind of break down the particle size so it can be accessible. At this time, you can separate the fats and oils because they float to the surface. And in a lot of ways, this is really what reduces the BOD and total soluble solids, because as you can imagine, solubles or insolubles, should we say, particulates carry a lot of BOD. So that's why it's so vital to do. You can't just pass it through the system. Now, as I mentioned, the biological part of it, which is, I guess, the more interesting part, is basically aerobic or anaerobic. And what we really do with the aerobic system is when we want to do quick turnover, really rapid throughput, as you would do in a municipal system. But as I mentioned to you, in a lot of the smaller sort of scale wastewater treatments, like the having Wellington, or having Sleeman's, they're purely anaerobic. And you can do that if you've got a long time to treat, your week or 2 weeks. And what we're doing, I know I keep repeating this, is that we're converting the carbon and nitrogen and phosphates and nitrites and whatnot into biomass, which can easily be removed. And the biology of sludge is very complex. You know, you've got all kinds of things there, from bacteria to viruses, to fungi, to amoebas and things like that. And it's very hard to recreate. And as we'll talk about with sludge, it's one of those precious commodities now. So typically, I knew a sort of an apple processor over in Newcastle who used to make lots of sludge with his wastewater treatment. He used to throw it away. But in reality, there's a lot of demand for sludge because everyone's got a wastewater treatment. They want sludge because you kill off your sludge by basically starving it, putting chemicals like sanitizers down waste streams. And there's always this demand for sludge. So it's actually quite prized in a lot of quarters. Anyway, so in the aerobic process, what we're trying to do is convert the carbon, phosphate, and nitrogen into biomass. So the BOD goes into the growth CO2. And what we try to do is reduce it down to an acceptable amount, i.e. below 300 mg per litre. Now, the thing to remember is that these are living sort of beings kind of thing. So if you starve them, if they're aged too much, then the performance does waver. And sludge management, as I mentioned to you, is one of those big areas. Anyway, so we've got two processes, the activated sludge and the trickle filter. And in the activated sludge, what we try to do is build biofilms again. But it's not like vinegar production where you basically have this thin biofilm on the surface. You just want aggregates because they give you good settling. You know, if you have a very fluffy, these microbes going everywhere without being connected, that's called poor settling. And I know I keep repeating, good settling is good for a simple reason: you're taking the biomass out very quickly, you're settling it quickly. So that's why you need these biofilms and things like that. Now you can mechanically aerate it, or you can sparge it. Usually sparging is more efficient, and you know, as I keep going on about, it's really impressive to see the ones in Guelph wastewater because of how much energy it takes to aerate the basins. And so typically the sludge you produce goes to disposal in terms of the anaerobic digestion. But as I mentioned to you, it's very highly prized in terms of going to a wastewater treatment. In Guelph, for example, and the consortia you have is important, obviously, because you want to make sure it's definitely denitrifying. And they had this isolate they actually bought from Europe, which was really good at denitrifying wastewaters, and it cost them $85,000 for this sort of bacterial strain. They lost it, but then they bought another one and they added to it. So as I mentioned to you, you can tinker. The sludge is critical in terms of it really defines what the process is. And there's this sort of business, side shoot business going on where people are trying to sell designer sludge and things like that, which is enhanced ability to denitrify and things like this. Anyway, I'm digressing a bit. So basically, as I mentioned to you, you've got to be very careful on how you nurture your sludge. And this comes down to the loading rate of retention. So it goes without saying, if you've got very poor BOD or poor nitrogen, poor phosphate, then your sludge is going to suffer, i.e. it's start going to be starved off, it's start going to die off, it's going to go into dormancy, which isn't good. For the simple reason it's not doing its job, is it? But if you've got a very high volume and very high biosolids in, you know, you can get this disruption in pH, for example, or ammonia production or whatever it is. And other than that, if you've got a very high rate, the microbes haven't got time to act. So you basically, your treatment's not going to be effective. And as we mentioned, there's not much after that treatment which can reduce the BOD, so you kind of circulate it back in. And this is why, for example, you might hear stories about Up in Montreal, for example, they put a lot of raw sewage into the St. Lawrence. It's not because they're doing it because they're lazy, it's because they know their wastewater plant is over capacity. And so they can't, and so they'll rather dump it in, raw sewage into rivers rather than, as I mentioned, overload the treatment plant. And so this is a typical picture. I don't think this is Guelph, but it's very similar size. You've got these basins which use got aeration underneath. It's like a bubbling bath, and you get all the biofilm forming. And as I mentioned, it goes into a settling tank where you hopefully settles that out, and you can take that to the digester. So you might have seen these, as you say, when you're coming over in a plane, they're landing in Toronto, these big basins. It's all to do with a bit like what we say with Southerners in terms of good aeration, homogeneous, which is essentially stirring. It makes the conversion of the carbon nitrogen phosphate into the sludge, which is then picked up at the secondary sludge tank, which then goes to the anaerobic digester. So the thing is that, as I mentioned to you, it's very complex, and what you have to do as an engineer is control the sludge loading rate. So this sludge loading rate is the amount of biomass, or the BOD, i.e. how much biological organic, what's the biological oxygen demand, over the biomass versus time. So it goes without saying, doesn't it? If you've got very high BOD, very small biomass, your sludge loading rate is going to be high, and vice versa. If you've got very low BOD, high biomass, it's going to be very low. So that's the loading rate, which you kind of control. And then you've got your retention time. So this is the mean residence time within the actual basin. So it goes logically, doesn't it, is that if you've got a long retention time, you're going to get more conversion of carbon to biomass, isn't it? So typically what you would do is it's a semi-continuous process in that you feed it in like a, as you feed in, you get sludge coming out, and that sludge goes to, as I mentioned to you, the anaerobic, it can burn it, or more typically they'll take it to anaerobic digestion. So typically what you get then is a typical process would have a sludge loading rate around about 0.25 to 5, and the treatment time would be around 6 to 12 hours. So what you'll get there is BOD removal, because it's going to biomass. You get nitrification, your nitrates going into biomass in terms of amino acids and whatnot, and you get average sludge formation. So sometimes you want to go extended though, and the reason why you go extended is, as I mentioned before, nitrification and taking the phosphate out can be very tricky, because you've got to have special microbes there, denitrifiers. And as I mentioned to you, Guelph Wastewater, they spent $85,000 on isolates to do this. And you can see why the benefit is, because if you've got shorter HRTs, the more throughput you have, and therefore the less wastewater blueprint or footprint you need. So typically an extended one would be used when you've got high nitrite, and what they do is they actually measure the actual composition of wastewater coming in. It's not just a simple process. This is why, it literally is. So the person who manages it was telling me he's on alarm, and if it at 3 o'clock, if there's some kind of incident, he literally has to get up and go and take care of it. And it is a kind of what is it? A stage career in that you're looking after sludge all the time. Anyway, so yes, it's extended, but you can get high rates. So with high rates, it either means you've got a lot of volume or high BOD and as I mentioned to you, I think with the melt coming, this is what will typically happen. And typically what you would have then is that you'll have low hydraulic retention time, for the simple reason is that your volume coming in. And as you could imagine, that means the BOD removal is not as much, and nitrification not so good, and you get fairly high biomass because of the nutrients there, all of which puts a strain on the system. And this is why, for example, you do get occasions where they'll literally put raw sewage into St. Lawrence and things like that. But according to the Guelph, they never do that. Well, of course, not on the St. Lawrence, I guess. So, I think I've said this. So what situations would result in increased sludge loading and short HRT? Is it high volume of wastewater, low volume of wastewater? Would it be because there's a lot of pathogens in the wastewater? Is it low biomass within the reactor? Is it some of the above, but not all? So as I mentioned to you, what you'll do in practice is you'll balance out the sludge loading rate and also the retention time. But what would cause, and I think I mentioned the answer already, but what would cause it? Would it be high volume of wastewater, low volume, instance of pathogens, low biomass, or is it some of the above? Have a look. All right, so essentially what it really would be is basically high volume. Certainly low volume of wastewater does have a negative effect as well. And what they would do in Guelph is increase the HRT and also maybe decommission one of the activated sludge tanks. Pathogens in wastewater, obviously, they don't care much about them. But the low biomass within the reactor, it would be the opposite. As in, if you've got very low biomass, you would need very high retention times for it to work. And, you know, I know I keep repeating it, but it is that once your sludge starts aging, it really does negatively affect things. And as I mentioned to you, you have to feed it right back into another basin. It really disrupts things if the process doesn't work too well. Anyway, so as I mentioned, so the old method of doing it is trickle filters, which are ill-defined and not very easy to control. And what we do here is very similar to what we did with the vinegar production. Is we trickle down the feed, the effluent, through a bed of stones or clinker, whatever you want to call it, which is coated. Oh dear, which is coated with biofilm. And these biofilms take weeks to develop. And the reason why there's such a headache to work with, because people put sanitizers, acids, all kinds of things down the drain. And if you're working with a trickle filter and someone puts a load of acid down it and you kill off most of the microflora in that bed, it takes up to a year, maybe even longer, for it to actually develop the biofilm again. Whereas in the activated sludge, as you can imagine, all you have to do is get new sludge. That's why it's so priced. So trickle filters, and even though they sound good, and I've seen them actually used in small plants which serve industry, they're very susceptible to being disrupted. But typically you'll get these biofilms formed which take out the carbon, and you get the sludge sloughing off, and then with the sludge you then take it to anaerobic digestion. Pros and cons. So they aren't as sort of controllable. So and what we can't do is talk about sludge loading rate, but what we do talk about is organic loading rate, which is similar. You know, basically we talk about how much BOD per volume per day. Now, if you overfeed it, the biofilms form and they kind of block everything. You get a flooding event, which isn't good. So you need even more control, I would suggest, in this treatment than you would do an activated sludge process. And as I mentioned to you, if you do lose the biofilms on the clinker or rocks or supports, then you've got to build it up again. It can take weeks, if that, to do it. And so and again, you know, if you underfeed it, it's the same thing. It starts dying off with lack of nutrients. So it's one of these kind of pros and cons. And what you can do, though, is increase the surface area by using more defined plastic supports rather than just stones. And it is effective. It's just the reality is that it's very hard to control and very susceptible to failure. All right, so once we've made our sludge, what we're going to do next is that we could dispose of it. And in Guelph, for example, if you do go to the wastewater treatment, you'll see this big blue building there. And that used to be the composting centre. So what they would do is take the sludge and compost it. Now, for whatever reason, they discontinued that 20 years ago, but they kept it there. I think it would have been knocked down by now, but who knows. But typically what you would do is you want to reduce the volume of that sludge because you want to reduce the waste. And also what you want to try and do is produce energy, biogas, in the form of methane. So typically what we'll have now is that sludge, which is microbes and precipitated out organics, etc., go into this what we call blue box, which is just basically a reactor. And these are kind of semi-continuous in that the ones in Guelph, for example, you put the sludge in and you'll leave it there for 14 days and then withdraw it. It does take that long to actually break everything down. And you'll get, at the end of the day, carbon dioxide and methane. Now, the thing is that you can use the methane as biogas, but it needs treating. It reminds you of when Sleeman, say, first put their wastewater treatment in, because that was their initial idea, saying what we could do is take the methane from the biodigester, to heat up the kettle, things like this. What they forgot to do is take out the hydrogen sulfide, which accompanies the anaerobic digestion. Hydrogen sulfide is very corrosive, so it literally corroded the internal parts of the recovery system. But what you'll notice when you do drive past wastewater treatment, you don't see these flares and flames anymore because they do recover the methane, but they recover it, they have to dehydrate it, then withdraw the hydrogen sulfide from it in order to use it as energy. And it's not cheap, but nowadays with the energy costs what they are, it's become cost effective. So that's why you'll never see flames coming from the wastewater works unless it's on fire. Hopefully not. So basically the anaerobic digestion, I would go as far as say it's one of the most interesting biological processes you'll ever encounter in fermentations, because it's this succession, it's a combination of different microbes which are very hard to recreate, but they seem to naturally evolve, and I mentioned to you with sludge, it takes a long time. So typically when you do get sludge kill off, which can be done by starvation, acids, sanitizers, you go and buy your sludge rather than try to develop it again, because it does take a long time to develop, but once it's developed, it kind of in this sort of synchronization, I'll call it. So what you have is three basic groups. You've got the first group, which basically produces these short-chain fatty acids. The acetates of butyric acid, the propionate. So they're taking the fats, lipids, proteins, and carbohydrates to produce these short-chain fatty acids. And they're acted on by the acetogenic group, which basically take them, the short-chain fatty acids, and produce acetic acid and carbon dioxide. Now, once you produce this, then you get the methanogenic bacterial group working. And methanogens are very sensitive to oxygen. Like if you expose them even briefly to oxygen, they just die off, which isn't a good thing. But what they do is they'll take the acetic acid and they'll produce the methane and the CO2. And then you get the hydrogenophores, which take the hydrogen, which is from this part here, with the carbon dioxide to form methane as well and water. So like I mentioned to you, you get about 70% recovery of methane from these this sort of consortium of microbes. So typically then what you get is sludge, basically microbes, which are basically made up of lipids, carbohydrates and proteins are broken down, and then they get converted to the short-chain fatty acids, which then get converted to methane, which we can use as energy as a biogas, isn't it? So here's a schematic, and as I mentioned to you, if you drive past, I think I was going to drive past Guelph Wastewaterworks now, any wastewaterworks will do, you'll see these big fermenters here. I think in Guelph there's about 6 of them, and they vary. So they just look like, they don't always coloured blue. I don't think the ones in Guelph are blue. But what you have is you've got your substrate flow. So this is going to be your sludge, isn't it, from your settling tanks or of your anaerobic digester. No, the pen's not working. I don't know if you'll see that. So basically that introduces the sludge, and what you'll get is this natural settling. So the settling comes down, but then it starts to act. It starts to act into over 14 days to break down that sludge into methane. Now, it is an insulated process because what you have to do, it does generate heat, as you can imagine, any fermentation would. But it's important to keep it within a certain tight zone, around about 32 to 42 degrees C. And so what you'll have are these heat exchangers doing typically the cooling it down rather than heating it. But you can imagine in the midst of winter, you don't want it freezing. So you've got this insulation. And what you can also do, as I remember, is you can undergo what we call thermophilic anaerobic digestion. So thermophilic anaerobic digestion is a similar principle, except you use temperature at 50 to 60 degrees C. So the advantage of thermophilic digestion is that it's much more rapid. It takes a few days rather than 2 weeks. And as you can imagine, it's very unstable. Things die off fairly easily. So typically, though, you would just use the 31 to 42 degrees C. So what you get then is you introduce the effluent, the sludge, as we said, and it starts breaking down. Obviously, you get the separation of the water. So the water rises to the top, and you can take that off and then go for tertiary treatment. Your gas obviously rises, and that's the biogas, as we'll call it, which you can recover now, and you treat it, then you kind of use it as an energy source. And typically what you have to do is you mix it, but this mixing isn't for aeration, is it? This mixing is so you don't get too many dead zones. And what you'll get is this sort of continual removal of sludge at the same time, so it doesn't overbuild up. So you actually do inject air into the, I'm trying to get let's see if this works. Oh yeah, there you go. So they do inject air in, but it's not for aeration. It's basically just to move the excess sludge out, which then goes to the dewatering facility, which is essentially where it's pressed between two conveyor membranes. The moisture squeezed out, leaving kind of dry biosolid. So you draw off the gas, as I say, you recover it these days. Your wastewater goes to tertiary treatment. You've got insulation. And as I mentioned to you, it's a very slow process, but effective process. So the different microbes within that is very diverse and broad. And essentially the Clostridia take up most of the sort of role in terms of they're the ones that make these short chain fatty acids. So you've got the protease, cyclases, lipases. Acidogenic Clostridia, acetobutyricum, for example, that would take the butyric acids and or they'll produce convert all the sugars to the fatty acids or butyric acid and things like that. And then you get acetogenic bacteria. And these aren't obviously acetic acid bacteria because they need aerobic conditions. These acetogenic bacteria convert those fatty acids into acetate. And Phynototromus is one of them. And it's an interesting one, this microbe, in that it's in the family of Clostridia, even though it's a gram-negative, which is a bit counterintuitive. But it's got this metabolic pathways where enable it to metabolize fatty acids into acetate, CO2, and hydrogen. Phytrophoman, and that's something like that, isn't it? Anyway, so once you produce the acetate and the CO2, that's acts on methogenic bacteria, as we mentioned, to produce the methane. So, as I mentioned to you, one of the big holy grails of wastewater treatment is to produce a sludge that's going to be very effective at biogas production. And as I mentioned, and I will keep mentioning it, Guelph literally bought this straight for $85,000 to do the denitrification. But why do you think it's such a challenge? Is it because, well, if we do design a sludge which maximizes biogas, it's going to be expensive? Is it because a high proportion of the microbes are non-culturable? Is it because the populations are dynamic and change with time? Is it all of the above or just some of them? Oh, a bit of a mixed bag. So let's see. Yeah, it's all the above. So the thing is, it is expensive to develop these, because if you imagine having to get all these designer microbes and put them together, it's going to be more expensive than buying a ton of sludge from Guelph wastewater, isn't it? Also, a high proportion of non-culturable. We talked about this, didn't we, in the first lecture? A lot of the microbes there can't be cultured, therefore can't be characterized. But what's another critical part of it is that we get these dynamics in populations. So again, you know, sludge is literally a balancing act. So you've got a group of microbes producing all these acids, and you could imagine if they go overboard and produce too much acid, too much ammonia, that's going to affect the other microbes as well. So it literally is a balancing act in terms of introducing the nitrate and just hopefully keep it all balanced as that. So you do get these, as you can imagine, one set of microbes producing substrate for another set of microbes. It will go in cycles. So this is the challenging part. And obviously the other part about it is bacteriophage attack, very much like vinegar production. And that with vinegar production of this wild consortia, isn't it? It's broad consortia. It's very similar to that in wastewater. So the thing is then, when you're choosing between an aerobic and anaerobic process for your wastewater treatment, it really depends on the requirement. So, for example, if you've got a very short time of high volume, you would use an aerobic process because we know that produces biomass very quickly, it completes CO2, and you get a good conversion. But if you've got quite a bit of time and you've got low volumes, then anaerobic process is fine because takes longer for a start, but it's much less costly, isn't it? Because you don't have to aerate things, and you can get even methane to recover and things like that. So once your sludge is produced, what you probably do is try and thicken it. So the thing about sludge, it can be very, I know we talked about settling, isn't it? So good settling is when it's very compact. You know, it's a bit like peat, it's like soil. But typically when you get secondary sludges, because they're in a biofilm, it's very fluffy. It's a bit, I won't say a mousse, I think that's the wrong term, but yeah, very similar to that. And so it's difficult to thicken because it's like thickening a milkshake. It doesn't happen very easily. So what they'll do is dewater it by pressing it between two belt filters, and it just, like say, excludes the water and leaves the dehydrated biosolid. You can centrifuge, I haven't seen that. Such thickening where you basically can add coagulants or a sodium or lime to stabilize it. And then once you've got the sludge, you can do several things. So in Guelph, for example, years ago, they used to compost it. They actually had burning, I think, before then, which obviously doesn't go down too well now. Or you can chemically oxidize it. But typically what they'll do, for example, I know I keep going back to Guelph, but in Guelph, they'll just take the biosolids, they won't chlorinate it, they won't do anything to it, dewater it, and then inject it under the ground. So, because you don't want to start transporting water everywhere, do you? So we dispose of it, like I say, you don't incinerate it now. You probably fertilize it, but more likely, because it's so highly loaded with pathogens, probably inject it under the ground. Now, tertiary treatments are the final treatment. So you can imagine water coming from the activated sludge process. You can imagine water coming from the anaerobic digester. And they'll have fine organics in there. So we just need to polish it, as we call it, before disposing of it. So what they use for this is contractors. And if, I talk about Guelph all the time, but if you go to Guelph, they've got about 30 of these contractors right at the back in these grey tanks. And what they are is these discs, they've got these discs which rotate. And these discs form biofilms on the surface. So when they're out of the effluent, that's where they get the oxygen. But when they're in the effluent, that's where they're getting conversion. So you get your influent, i.e. wastewater, coming in. These rotate round. And as they rotate round, the organics, carbon, and also nitrogen and phosphate, get converted to biomass, which grows the biofilm. and these accumulate in these baffles. Now, the ones in Guelph, because of the efficiency of the wastewater treatment, I don't think they've been used for years. I don't know if it use them sometimes, but essentially they're just like a landmark, if you like, and you can see them there. So typically then this is just to remove those fine carbons before disposing into the, well, chlorinating, then disposing into the river. Now, as I mentioned to you, they've got very strict regulations in terms of wastewater. So if you're operating a plant, brewery, processing line, whichever you are going to look at, you have to reach these stipulations. So, for example, BOD, any one day you're only allowed 0.6 grams of BOD, or 600 ppm, isn't it, of BOD. But over the time course of a month, it has to be at that 300 ppm state, or 0.3 grams. Total soluble solids and pH, which is invariable, isn't it? So you get good days and bad days, but they're constantly monitoring. They're very, like I say, they've got all these sensors in the sewage pipe, so they can trace back to somebody doing something wrong very easily. You've got to meet these standards. And if you don't meet those standards, then you pay surcharges. As I mentioned, this has really got significant over recent years, in that they basically will charge you for excess BOD, total soluble solids, total phosphate, and what we call total coal-gel nitrogen, which is basically inorganic nitrogen and organic nitrogen. So if you're found to excess here, then you pay a certain surcharge. And just to illustrate how significant that could be, say you've got a small brewery, and as I say, it's very high BOD. The volume of wastewater and the BOD can lead you to something like paying over $500,000 a year in surcharges, fines. That's not if they close you down first, because they're very good at giving red cards out, as I mentioned. So because of this increase in surcharge, it really did increase the need to have in-house wastewater treatment. As I mentioned to you, Siemens really led the way here because, as I mentioned years ago, the growth of Guelph was restricted, not by the land, but by the availability of water. So the city actually, and it's true, they paid Siemens to actually install this wastewater treatment facility. And it does save them lots of money. They said it paid for itself. Well, it paid for itself because Guelph paid for it, I think. But it can save a lot of water. And this water can be used not so much to put back in the beer, but used for sanitation, cooling, things like that. So what you'll notice, as I mentioned to you, is in careers, the water manager will become a sort of official position, I think, because what companies want to do is reduce the amount of water they use, and obviously reduce the amount of water going into the municipal system, because they have to pay for both. And this is called water management. So water management wants to reduce the water usage, if we can, by using water-free processes. We want to get byproducts we can, rather than stick down the drain. So when you've got some yeast, for example, left over from a brewing batch, you don't want to put it down the drain because it's going to increase your BOD. But what you could do is reclaim that yeast and sell it as animal feed. There you go. You can prevent contaminants entering the water by trapping them. You can treat the water on site, which, as I mentioned to you, is very common these days. And you can practice water recycling, and we'll talk about water recycling in a bit. So the way you do this water management is a bit like HACCP in a way, in that you prepare a schematic of your facility in terms of each process, and then you identify what goes in and what comes out. So how much water goes in, what's the output. Then you do a water balance or strength and volume. So each of these processes will have different volumes, they'll have different strengths. And when we talk about strength, we're talking about BOD. And what we want to do is rank them. So we're really saying here is saying, well, which is costing me more? Is it, and it's the largest volume with the largest BOD process, where you would then focus on that thing. How can we reduce water, how can we treat it so we have low volumes going into our wastewater plant, and then figure out how to reduce the inputs as well. Is there any alternatives? So as an example, and it applies to everything, it's not just, I know we talk about brewing a lot, but in brewing, for example, water management is critical in brewing. As I mentioned, you try to get down to 3 or 4 litres of water per litre of beer, which is quite an achievement when you think about it. But this is basically your schematic then. So you've got the different treatments, and you, as I say, you list the input. Well, it's going to be water, isn't it? We're going to sanitize it. And what we're going to get from it is spent grain water, residual water, that is, rinse water and sanitizers. And you go through all the process in that manner. And then what you do is that you take samples of those wastewaters coming from each of those processes. You do what we talked about, measure the BOD, the COD, the total solubles, and the sanitizing agents. And, you know, I know I keep going on about it, but the biggest sort of problem you have with a in-facility wastewater treatment is sanitizers getting into the biodigester. You know, as I was mentioning, I know this chap in Newcastle, this apple processor, and the sanitation crew always used to forget to divert the sanitizer waste into another tank, and it used to go into the biodigester, and he literally used to have to change it nearly once a week in terms of the sludge. So you try to avoid that. I won't go too much here, you can look at your own leisure, but I think you get the idea, isn't it? Is that you've got these different processes, each one will contribute to the BOD. For example, as you would imagine, Whirlpool, which is the cooling part of it, the wastewater coming from there will be fairly high, but obviously the highest will be things like the kettle, you know, which has got all these extractable sugars in. So it goes without saying that you would focus more on the kettle in this case, and then you'll rank them accordingly. And as I mentioned to you, the sanitizer sort of wastewater is held separately for the simple reason is that, as you see, the sanitizer will kill off things. So you might have to use alternative methods for this, and we'll talk about how we can use physical methods, things like that, in order to clean it up. But certainly what you try to avoid is sanitizers getting into your sludge digester for definite. So when we talk about reducing the inputs and outputs, is that what we're trying to do here, isn't it? Is saying, can we do something to reduce the water going in? Now, it is a balance because obviously you need a certain amount of water, isn't it, in order to do a job, which is, and if you underdo it, so for example, with sanitation, if you haven't got enough water to rinse, then you're going to get residues of sanitizer, detergent. So you try to get it to the point where it's just working. So you're reducing volume, but you also, what you can do, isn't it, is reduce the amount of organics going down the drain. And to do that, it's very simple, isn't it? You can, one, minimize the concentration of detergents and sanitizers, so you don't use excess, but again, use it enough to be effective. Or capture the solids going down the drain rather than putting in, because I know, for example, when we're home, isn't it, and we've got some stuff in the sink, we try to push it down the sink or waste disposal, you know, rather than collect it and then put it into the sort of recycle bin, isn't it? So typically this is what you do. So you get things like traps, for example, you know, these traps which will stop particulates going in the drain because particulates contribute to the BOD. Things like mesh on, you know, on these sort of floor drains. Again, it might look trivial, but most of the BOD and COD are kept up in those particulates that you can remove. So typically then, if you've got high BOD, as I mentioned to you, it can be a good thing because that means you can use your biodigester efficiently because biodigesters are living cultures. But after saying that, you've just got to be careful with it because you can't overfeed it and you can't underfeed it. It's a bit like everything else, isn't it? Everything in moderation. So it has to be consistent. And the problem with these small facilities is the demand for wastewater gets changes through the day, doesn't it? You know, as you're producing, you're wastewater could be high with a high BOD, but then on the times when the processing line isn't working, it's going to be very low. So what they'll typically do, they'll store it and try and even it out. So for high and low, and then try to separate out, as I mentioned, the sanitizer streams and things like that. When they do have sanitizer, though, they'll try and dilute that out if need be. You know, it depends. You just want to avoid shocks. You want to feed in consistently, is the word, isn't it? And as I say, you remove the sludge as you do, but if you get too much sludge in a reactor, it starts blocking and things like that. So you've got efficient removal. And then you can also control disposal of the residual effluent from your biodigester into the sewage system. So again, you store the water and kind of bleed it in from high times to low times, things like that. Like I say, the beast to manage. So what we'll do is we'll finish off with the microbial membrane bioreactor. So MBRs are very common and in small facilities. So when you go to a facility, you can have a look for their wastewater system, and typically the MBR reactor is compact, it's efficient. So normally what you'll do in wastewater is, as we talked, I don't bore you again through it, you just get solids removal, you settle in to get rid of some of the solids, then you put it into the aeration tank, and you'll settle it, and you'll sand filter it, and then you'll disinfect it. Now, with an MBR, what you tend to do is quicken the process up, and the way you quicken it up isn't so much the aeration stage, but having a membrane, a RO membrane, or microdialysis membrane, rather than settling. So as you can imagine, it quickens the process up because you're physically separating it rather than waiting for gravity to do its thing. Now, the problem with it, though, is that it gets biofouled very easily. So when you get polysaccharides formed, it blocks pores and things like that. But it's very efficient. And what you end up with sludge, and that sludge can be, again, sold, you know, to feed other sort of digesters that's out there, and the effluent coming in. So it only takes a relatively short time to treat, and it's what, as I mentioned, you'll probably see as you go along. So why do you think, though, is that these membrane bioreactors use an aerobic step rather than anaerobic? Is it because it's lower cost? Is it because you get rapid conversion of organics to biomass? Is it complete oxidation, all of the above, or some of them? So in some places, you'll just see anaerobic digesters, but with the MBR, they usually have an aerobic step. They don't have typically a anaerobic step, and because they sell the sludge literally on the market. So, but why is it aerobic? Oh yeah, I suppose you got it right. So it's not lower cost, it's definitely more expensive. Anything with aeration is always expensive, but it's this rapid conversion, it's almost complete oxidation. Because at the end of the day, what you're trying to do is reduce the BOD, isn't it? So typically then, when we're looking at reducing volume, you know, essentially what we're really saying is that we reduce the barrel of waste. And in beer production, for example, it goes without saying, if you could separate the yeast from the beer effectively, you're going to have more beer, isn't it? So you're not throwing that down the drain, you're selling it, and you can take off the yeast. And even fixing leaks and low pressure hoses can bring back significant changes, because lower pressure, lower volume being used, leaks go without saying. And recycling of the water and sanitizers. So again, it's a balancing act, because I've seen occasions where they try to recycle, and essentially the sanitizers degrade, I sequester, and it's not effective. And you can get issues with recycling water because, especially chemicals and taints. So it's, even though it's kind of not nostalgic, I suppose the word is that looks economic. You've just got to be careful what applications you do. You would never recycle water, for example, directly in contact with a product, because I think you would be really asking for trouble then, isn't it? So typically then what we'll start on Thursday, it's Tuesday, isn't it? we'll talk about how we can develop a small water recycling system and how the different options we have. But I think we're I guess it's time. So we'll leave that for Thursday. So just to remind you, we need to get the midterm exam in by midnight, and then I'll mark them and we'll see how you've done.
Thank you.